As I said, when we studied rational expressions and rational functions and rational equations in 30-1, we learned about horizontal asymptotes, and I would have explained to you in terms of a limit what a horizontal asymptote is all about without actually using the word limit. And then I gave you a shortcut rule, which we're going to review today, for determining the location of a horizontal asymptote. And the thing you need to understand is that shortcut rule, and that's what I will call it to remind you of what I'm talking about when the time comes. What you need to know is that shortcut rule is limited. It cannot be used all of the time to find all horizontal asymptotes. And in fact, the more general procedure that I'm going to teach you, even that can't be used all of the time. So there are limitations to how we find horizontal asymptotes. To begin with, the definition of a horizontal asymptote is that if the function, and I put in brackets in your notes here y, because when we talk about a function, we're talking about the value of y on a graph. If a function approaches some value as x gets extremely large, which means x is approaching infinity, or as x gets extremely small, and I'm using small in the purest mathematical sense here, meaning x is approaching negative infinity. I'm not talking about it's approaching 0. It's approaching negative infinity. If y starts getting closer and closer and closer to some particular number, some value, as x takes off to the right or to the left, then there's a horizontal asymptote at that location. And if I say to you that that value of y that the function is approaching is L, then that means the limit as x approaches infinity of the function equals L, or the limit as x approaches negative infinity of the function is L. And this is primarily how you determine whether there's a horizontal asymptote. You find the limit as the function, you find the limit of the function as x approaches infinity. There's a certain procedure to it. So as an illustration here, there's a function. It's neither odd nor even. There does happen to be with this function a vertical asymptote, but I don't care about the vertical asymptote. What I care about is the horizontal asymptote. We've already studied the vertical asymptote today. I could say at whatever that a value of the asymptote is, I could say that the limit as x approaches a from the left is positive infinity because the graph is going up. I could say that the limit as x approaches that non-permissible value from the right is negative infinity. But again, I'm here right now to talk about horizontal asymptotes. So you will notice that there is a horizontal asymptote there. I'm going to mention this now and then explain it in more detail later. The weird thing about horizontal asymptotes is that the function can actually cross the asymptote. When you have a vertical asymptote of a function, that's a non-permissible value for x. X will never be that number. But when you have a horizontal asymptote, y can actually have that value. And you can see here 2 points actually, this point on the function and this point on the function, where the graph actually has that y coordinate that is the location of the asymptote, the horizontal asymptote. What is important is not the behavior at any particular point, it's the behavior to the left and the right. So that's the horizontal asymptote at y equals L. If you take a look at x getting larger and larger and larger as x approaches infinity, you can see the graph approaches a value of L. I admit I'm using a non-traditional mathematical statement there. Normally, you would simply write y approaches L. but I want to reinforce to you that the graph is getting closer and closer and closer vertically to the value of L. What does that mean? It means that the limit as x approaches infinity of the function is L. On the left-hand side, and again, I'm using a non-standard mathematical notation here, I'm saying as x gets closer and closer to negative infinity, and it's written backwards because x is going to the left, then y will get closer and closer and closer to L. And that means that the limit as x approaches negative infinity is also equal to L. Now, sooner or later, somebody's going to wonder, does the asymptotic behavior on the left have to mimic the asymptotic behavior on the right? What do I mean by that? I mean, does the limit as x approaches negative infinity have to be the same as the limit as x approaches positive infinity? The answer is no. There are rare cases, and we're sure to encounter a couple of them in the next week or so, where you have a horizontal asymptote at, say, y equals 2 on the left-hand part of the graph, but on the right-hand graph, you have a horizontal asymptote at y equals 3. They could be different values. All right, functions can cross horizontal asymptotes. I want to explain to you why, because it is a little bit worrisome that they do. The reason why a function cannot cross a vertical asymptote, so right now what I am looking at, everybody, is this vertical asymptote here. The reason why a function cannot cross that line is because functions only go up and down. A function is not allowed to go back and forth. And if the function is approaching the asymptote on its way up and approaching the asymptote on the way down, and a function is not allowed to go left and right, it only goes up or down, you can't cross that line. On the other hand, if I take a look at the horizontal asymptote of this function, which is this, functions are allowed to go up and down all they want, and this function happens to go down and then goes back up. As long as it's asymptotic as x approaches infinity, it's allowed to do whatever it wants anywhere else, because functions are allowed to move up and down. They can't go back and forth because then they would fail the vertical line test. I have a more interesting graph that we can look at. Which is this one. This is asymptotic. The equation of this function is 25 over x times cosine of 0.5x, I believe. I just want to check. Plus 5. So there's some other parameter in there. And if you take a look at what's happening to this function, there is an asymptote at y equals 5. And when you follow the behavior of this graph, it goes down through 5, and then it gets closer to 5, and it gets closer to 5, and it gets closer and closer and closer to 5. It will never end up, if this is the asymptote, it will never end up doing this and getting closer. But each time it crosses an infinite number of times, each time it crosses, it's going to get closer. So by definitions in mathematics, that line is asymptotic. Okay, so we're just going to use a very important property of limits to determine limits as x approaches infinity. And as long as in this definition, r is a positive rational number. What do I mean by that? I mean we've got 1 over x to the r, and r is a number like 5 or 10 or positive 0.6. But it's not negative, it's not 0, and it's not an irrational number, because irrational numbers do goofy things sometimes, then that limit is 0. And I mean, just think about this. If I said to you that we want to take the limit as x approaches infinity of 1 over x, well, as the bottom of this expression, the expression is 1 over x, as the bottom, which is x, gets infinitely large, the entire expression gets infinitely small. That's how fractions work. 1 over 10 is small. 1 over 100 is smaller. 1 over 10 million is even smaller. So as x gets infinitely large, the entire expression gets infinitely small. And infinitely small in this context is 0. If I had 1 over x to the 3, that's not going to change the argument, because the bottom is still going to grow infinitely large. By the way, and it could be a decimal, we can extend this to things like the following limit. What if we had 100 over x squared? Well, this is still going to be 0. And there's two ways to understand that. One, as x gets infinitely large, the bottom gets infinitely large. And I'm not going to write infinity squared, because it's infinity. It's as large as it can be. The top is 100. Well, I don't care that the top is 100. The top compared to the bottom is 0. It's nothing. Okay? Another way that you can show that this is still 0 is to remember that a limit of a constant times a function is the constant times the limit of the function. And if you know that this is 0, then we have 100 times 0, which is still 0. This rule is also true when we take a look at x approaching negative infinity. What is important is it's some non-variable fraction over the variable raised to a positive exponent. We're going to use this idea to find limits. So algebraically determine any symmetry, asymptotes, extrema, and also sketch the function. I haven't decided whether we're going to sketch it or not. So let's do the symmetry first. What I would like everybody to do is determine whether this function is odd, even, or neither without using a graphing calculator. And a lot of the work I would actually do elsewhere here, maybe on scrap paper, or if you're going to use the space that I've given you, you need to be judicious in organizing it well, because look at all the stuff we're going to have to do. So I'm going to show my work here. By the way, this is an even function. And the reason it's even is that f of negative x is 3 times negative x quantity squared minus 1 over negative x quantity squared minus 1. F of negative x is 3x squared minus 1 over x squared minus 1. But that is equal to f of positive x. That's equal to the original function. So this function is even. Let's determine the x-intercepts. Well, remember what I said. You look at the top of the function for x-intercepts. You look at the bottom of the function for non-permissible values of x. So looking at the top of the function, we're finding the values of x that make it 0. Those are going to be x-intercepts. Looking at the bottom, those are going to be asymptotes that are vertical or holes if any of the factors cancel. So when I look at the top, I'm going to have x-intercepts of positive 1 over root 3, comma 0, and negative 1 over root 3, comma 0. I don't really believe you need to show work here. I'm going to just squeeze my work for the x-intercepts above the question. You would take 3x squared minus 1, set it equal to 0. This becomes 3x squared equals 1. This becomes x squared equals 1 over 3. This becomes x equals plus or minus the square root of a third, and the square root of 1 is 1. The square root of 3 is root 3. But the y-intercept? Well, the y-intercept is found by putting 0 in for x in the function. And I'm really not going to show that work here. I will basically temporarily animate this function for you. If I put 0 in for x, 3 times 0 squared is nothing. 0 squared is nothing. I'm left with negative 1 over negative 1, which means that when x is 0, y is negative 1. So we have a y-intercept at 1. Negative 1 over negative 1 is 1. So the y-intercept is at 0, comma 1. Let's check these off. We've got the symmetry done. We have the intercepts done. Before we get into the first derivative, let's do the asymptotes. We will have vertical asymptotes at x equals 1 and x equals negative 1. Because remember, the non-permissible values are found by taking the denominator and solving that equation. I don't care how you solve that. You can factor x squared minus 1 into x plus 1, x minus 1. You can move the 1 over and go plus or minus the square root of it. Since the top is not factorable, but the bottom is, and I'll just squeeze this in here as x plus 1, x minus 1. Since these two factors on the bottom are not canceling with identical factors on the top, that means the non-permissible values correspond to vertical asymptotes. So there's no holes in this. Now the horizontal asymptote. We need to find the limit as x approaches infinity of that function. Remember, the location of the horizontal asymptote is this. It's the limit as x approaches infinity of the function. Now, I'm actually going to not show you the shortcut here. How do we do this? There's a rule, and what it is that you identify the highest degree of x in the expression, which is 2, and you rewrite the limit by dividing every term by x raised to that highest exponent. So we're going to write it as 3x squared over x squared minus 1 over x squared over x squared over x squared minus 1 over x squared. And we notice that if we do that, we can cancel some things. I can cancel this x squared and this x squared and this x squared and this x squared, which is going to give me the limit as x approaches infinity of 3 minus 1 over x squared over 1 minus 1 over x squared. But wait a minute. 1 over x squared, as x approaches infinity, this is 0, and this is 0. That's that rule that I talked about here. As x approaches infinity, 1 over x squared approaches 0, which means that this limit is actually equal to 3 minus 0 over 1 minus 0, which is 3 over 1, which is 3. So there is a horizontal asymptote at 3. Now the shortcut, I don't know if you remember this, but anytime the highest degree on the top matches the highest degree on the bottom, you can take the coefficient of the highest degree term on the top and divide by the coefficient of the highest degree term on the bottom. 3 over 1 is 3. So that's the horizontal asymptote. We've got that out of the way. Now we have to do the max mins. Now, keep something in mind, I talked about this before. There's one more step to graphing which has to do with the second derivative. So this may seem like a daunting task that we're responsible for doing here, but it will get even bigger later. So we have to differentiate that now. I don't know what your workspace is looking like. You might choose to do the derivative and the first derivative chart on a separate sheet of paper. I notice I didn't give you a lot of room in the handout. So the function is y equals 3x squared minus 1 over x squared minus 1. All right, so dy dx is the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. I'm going to double check my work. Looks okay. We always factor, I've been saying this from day 2 or 3 of this course. You always factor to simplify. I can factor a 2x out of the numerator, and out of the first term I will have a 3 and then x squared minus 1. So just to make sure, when I talk about out of the first term, this is what I'm left with. When I talk about out of the second term, when I take the 2x out, I'm going to be left with minus 3x squared minus 1. And this is over x squared minus 1, quantity squared. Double checking, I'm going to double check, by multiplying this through and by multiplying this through, just to make sure I go back to the beginning. I would get 6x times x squared minus 1. I would get 2x times 3x squared minus 1. So that's all good. Any questions to that point with the derivative, everyone? All right. I'm really tempted to kind of simplify that leftover stuff on the side, but I also know that that's where I'm liable to make a mistake. So when I FOIL this, well, FOIL's the wrong word, but when I take 3 times x squared minus 1, I get 3x squared minus 3. And then I have, be careful here, I have minus 3x squared plus 1. This is over x squared minus 1, quantity squared. So we're just about to the point where we can do our first derivative chart. I have 2x inside of the brackets, and I do want to check that, double check that step, 3x squared minus 3 minus 3x squared plus 1. It looks okay. Inside of the brackets, I have negative 2. Because the 3x squared minus the 3x squared is 0. Negative 3 plus 1 is negative 2. So finally, we get this for a derivative, dy dx is negative 4x over x squared minus 1 quantity squared. So why are we doing this? So we can do a first derivative table. The first derivative table is going to be constructed by identifying that you have a critical value of x of 0 for the numerator. You also have a critical value of x of 1 and a critical value of x of negative 1. The 1 and negative 1 come out of the denominator because x squared minus 1 is x plus 1, x minus 1. By the way, I don't know that you're going to remember this to check all the time, but this function had symmetry. So if you have symmetry and you have a critical value of x of a, you must have a critical value of x of negative a. All right, we're going to go from negative infinity. I'll draw this out for you. From negative infinity to negative 1, from negative 1 to 0, from 0 to 1, and from 1 to positive infinity. Again, lots of things we can do to kind of check our work along the way. One of them being how many critical points do we have, or critical values of x. If we have 3, we need 4 intervals. You want to make sure that you put your intervals in the proper order from left to right on a number line, even though we're writing them vertically. And then across the top, we can put our factors, negative 4x, and then x squared minus 1, quantity squared. This is dy dx, and this is y, and then we can come to a conclusion about max mins. Negative 4x is positive any place x is negative. So in those first two intervals, x is always negative, times negative 4 will be positive, and then when x is positive, negative 4x becomes negative. X squared minus 1 quantity squared is positive everywhere because of that quantity squared. Because of that squared, these must all be positive. And that's why I didn't bother to put in my table x plus 1 squared, x minus 1 squared. Or as I've seen some texts do, they'll write in a column for x plus 1, another column for x plus 1, a column for x minus 1, and another column for x minus 1. So multiplying across the top, we get positive for the derivative in that interval, positive for the derivative in this interval, negative and negative. So the function is going up here and here because the derivative is positive. It's going down here and here, which means we have a maximum at the critical value of 0, comma, some number. And now we need to find out the coordinates of that point. How are we going to do that? We're going to look at the function. So I'm going to put 0 in for x, and what we discover is that you get 1. In other words, everybody, this y-intercept, that's a maximum value of the function. The function has a maximum at 0, 1. While I'm setting this up to now draw it, I would like everybody to calculate the value of 1 over the square root of 3. We need to know approximately what this number is in order to sketch it properly. Okay, I'm going to put in my asymptotes first. We had an asymptote at and I'm going to be periodically checking in with you here to double check, we had an asymptote at -1 and at +1. Can you guys confirm that? Okay. Can somebody please tell me what you get for 1 over the square root of 3? Okay, so since that number is a lot less than 1, I'm going to move these over a bit. I want to be able to put in those X-intercepts so that I'm not crowding the whole graph into a very small area. So those two asymptotes are at 1. We also have a horizontal asymptote, and I believe the horizontal asymptote was at y = 3. Is that correct? Okay. So what does that mean? That means I have to scale things here. I'm saying that this is 1. This would be 2 over here. 1. This would be -2. But I'm scaling things differently here. I'm going to scale 1, 2, 3. You know, it's entirely, that may even be too high. It's entirely up to you. Okay, so we've got an asymptote there. And remember, the challenge here is for us to do this without the aid of a graphing calculator. Okay, let's start putting in coordinates of points that we actually know. We actually know the y-intercept is a maximum value. I'm going to put that in. I'm going to use a different color here so we can see it. This is a point that we know, and it's a maximum. We also know that you said 0.577, so 0.577 for 1 over root 3, that's about here, I would say. We also know there's a point here, and you know, if you have a ruler or something you can kind of use to estimate, we would like to make sure that we put the other point so that it's symmetrical. We don't use graph paper, so you're always kind of eyeballing things, but you can use a ruler to help you out. Now comes the challenging part. If you look at your first derivative table, correct me if I'm wrong. No, don't even correct me. Tell me in chat, in the first interval from -∞ up to -1, in that first interval from -∞ to -1, is the function increasing or decreasing? It's increasing. Okay, so what I'm going to do is just indicate that the function is increasing everywhere up to that point. Now we have another critical number at 0. Is the function from -1 to 0 increasing or decreasing? It's increasing as well. So up top, I'm simply going to put arrows that indicate whatever I draw in this region, I have to draw up. Whatever I draw in this region, I have to draw up. And then I believe when you check it out, and Dan, you can confirm this, that the final two intervals are decreasing, decreasing. Good. So this is at 1, and the function goes down, 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 down. So your challenge, and I'm not going to draw it for you right now, I'm going to give you a minute to think about this, is to draw a function that is asymptotic on all of those asymptotes that goes up, up, down, down. I think most people get that the graph in between is going to look like the following. That certainly satisfies the nature of the two vertical asymptotes, and it certainly says the function is going up and then down. That makes sense. How do you draw? And I'm not going to ask you to describe it, but I'm just going to ask you, how many of you know how to draw the other two pieces? Does anybody know how to draw the other two pieces? I'm not going to put you on the spot and ask you to explain it, because it's a difficult thing. The only way that these two lines can be asymptotes, the only way the graph can be increasing in this interval and be asymptotic to both of these highlighted asymptotes is if the graph looks like that. And left to right, the function is going up. And the only way it can happen here is that. If, everybody, the function up here was decreasing, it's not, but if the function was decreasing there, then your only option to sketch it would be to sketch that, in which case you will have known that you made a mistake, because that is going to have another X-intercept, and there wasn't another X-intercept. You got to kind of pull a Sherlock Holmes approach here to try to figure out how all of this can be true in order for you to get the graph. You just go back to what it was. So that's an awful long example. We have one more to go. And I don't know exactly what my plan is for Monday. I suspect that Monday we'll have a one lesson day. So this is going to go right till 3 o'clock, would be my guess. Any comments or questions on that first example? All right, let's try one more. This time it's x over x cubed minus 1. So I'm going to make a list of things here. Symmetry, X-intercept, Y-intercept, horizontal asymptote, which if it exists is that y equals something, vertical asymptotes, which if it or they exist will be at x equals something. And we're also going to want to know our derivative. This is kind of the template. You always want to get all of this information compiled to look at the graph. So symmetry, there is no symmetry. And I don't believe that I need to show my work to explain this. If it were a written response or an assignment, you obviously have to do this. But if I put negative x in for x, the top of this becomes the negative of what it was, and the bottom doesn't become the negative. This term will become negative, but this term will stay the same. You can also tell, I don't know, how many of you can tell that this is neither because there is a mix of odd and even exponents in the bottom? That's an interesting kind of idea, that if you have the top or the bottom of a rational expression and all the exponents are even, then there is some symmetry associated with that. If all of the exponents are odd, there's some symmetry associated with it. But 3 is odd and 0 is even, so there's no symmetry. The y-intercept is found by putting 0 in for x. I also believe that I don't need to show any work here, because if I put 0 in for x, this is 0 over 0 cubed, which is 0, minus 1. 0 over negative 1 is 0. The y-intercept is the origin. Whoops, I wrote my statement of symmetry in the wrong place. Symmetry, no symmetry. The y-intercept is the origin, which means automatically there's an x-intercept of the origin as well. In addition to that, you find x-intercepts by investigating the numerator of the rational expression. The value of x that makes it 0 is 0, so the x-intercept is 0. Vertical asymptote, you now turn your attention to the denominator and you say x cubed minus 1 equals 0. Well, that means that there's a vertical asymptote at x equals 1. Whether you solve that x cubed minus 1 equals 0 by factoring it using a difference of cubes, or whether you just move the 1 over and take the cube root, I don't care. You get x equals 1. Horizontal asymptote, we want to find the limit as x approaches infinity of x over x cubed minus 1. The highest degree on x is x squared, so we divide every term by x squared. Sorry, the highest degree is x cubed, so we divide every term by x cubed. What do we get? We simplify this, and the top of the expression becomes 1 over x squared. I can cancel an x with an x in the x cubed. The bottom is 1 minus 1 over x cubed, but at infinity, this is 0, and this is 0, which means this limit is equal to 0 over 1 minus 0, which is 0 over 1, which is 0. So y equals 0 is a horizontal asymptote. In Math 30-1, you were taught a shortcut was that if the degree on the top is smaller than the degree on the bottom, then the x-axis, which is y equals 0, is the asymptote. Now we have to find the derivative. Our function is y equals x over x cubed minus 1. I better just make sure that's right. I'm pretty sure it is, but it would be a tragedy to make a mistake at this point. dy dx is found using the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Double check my work here, meaning you should double check it as well. I think it's fine. There's nothing to factor out, so we might as well just go ahead and get rid of the brackets. X cubed minus 1 minus 3x cubed. The top is negative 1 minus 2x cubed over x cubed minus 1 squared. Are we in agreement on that? Take a minute, no rush. Double check all of the work on the derivative to confirm that you get the same thing. Haley and Rachel both in agreement? Dan's in agreement. Math is not a democracy, but as always, 20 eyes are better than 2. I'm pretty sure it's fine myself, but I would want to go one step further and factor that -1 out. Now I can identify my critical values of x. My critical values of x are 1 for the denominator, and again, 1 was a non-permissible value. So any non-permissible value for x has to be a critical number in the derivative. And then also the cube root of, well, there's a lot of ways to write this. I'm going to write it as the cube root of -1 over the cube root of 2. And let me explain my reasoning there. In the numerator, you have 1 plus 2x cubed equals 0 is what we're thinking, which means 2x cubed equals -1, which means x cubed equals -1 over 2. So I take the cube root of both sides, and the cube root of -1 is -1. And again, you don't have to write all of this down. I'm just explaining how I'm getting these. The cube root of 2 as an exact value must be left as the cube root of 2. We're obviously going to have to figure out what that number is approximately equal to answer the question in detail, but we'll get to that. So I'm going to go back to the first page, and I forgot to put squared here. That's important. And just put in my derivative, which was -1 times 1 plus 2x cubed over x cubed minus 1 squared. Can I get some people to double check that I transposed that correctly from the other page? Okay, thank you. All right, so we are going to slice up the number line using those two critical values of x. One was 1, and one is -1 over the cube root of 2. Now might be a time where we can calculate what that is approximately. So I would like you to figure out for me approximately, was it that 0.577? Is that the same number? Just figure out what -1 over cube root 2 is. Oh, it's -0.793. Can I get a couple other people to confirm it is? Okay, so it's very, very close to -0.8. I mean, it's not equal, but it's close to -0.8, which will be good enough for our graph. Okay. First derivative chart. -∞ to -1 over the cube root of 2. -1 over the cube root of 2 to 0. Nope. To 1, and 1 to infinity. Double checking a few things. Are my critical values in the right order? They are. Are my critical values correct? -1 over 2, take the cube root, and 1, yes, they are. Across the top, we are going to have -1. We're going to have 1 plus 2x cubed, and we're going to have x cubed minus 1 squared. This part here that I'm about to erase, I don't think you need to write it down all the time. Even if I were expecting you to show your work, this part that is being erased now is just there to make sure that we're not making any mistakes. So those are my three pieces of the derivative. And then I'm going to have a column for dy dx. I'm going to have a column for y. So negative 1 is negative everywhere. 1 plus 2x cubed, since it has an odd exponent on the variable, we treat it like a linear factor, which means it goes from negative to positive, and it crosses over when it passes the 0 of the factor. Again, feel free to just take a number. If you're more comfortable just taking a number that's in the interval and putting it in there and seeing what happens, do that. The third column for the factors is positive everywhere because it's squared. So dy dx is positive, then it's negative, and then it's still negative. What does that mean the function is doing? It means it's increasing, then it's decreasing, then it's decreasing. And that tells us that at negative 1 over the cube root of 2, we have a maximum value. In order to facilitate this moving a little more smoothly, I don't care about an exact value for y, but I do want us to calculate the y coordinate of that maximum value, which means you have to take negative 1 over cube root 2 and put it, in for x and calculate the y coordinate. I'll do the same thing just so we can double check each other's work. Getting about 0.53. Dan, you're in agreement there? I just caught that out of the corner of my eye. Yeah, good. So it's about 0.53. Okay. Now we got to put it all together. So we're going to sketch this. Again, I'm going by memory here, so I may ask you for your help rather than me flipping around. And I may not commit to where I put everything to begin with. I might move some stuff around. But I do know that the graph went through the origin. And I do know that there was a critical number of 1 and a critical number of about negative 0.8. And there was an asymptote. I'm just talking myself through this right now. Okay, so that's good. I can put the asymptote in. Was there also an asymptote at x equals 1? Good. So now I'm starting to get an idea of where I'm going to sketch things. Let's put 1 here. It seems to me that we had an x coordinate of negative 0.8 for a critical number. What I'm going to do across the top here is I'm going to put my intervals from my first derivative chart. And again, I'm using just the tools I have available. You could use a ruler. If that is positive 1, then negative 1 is over here. And negative 1 over cube root 2, remind me again, was negative 1 over cube root 2 approximately negative 0.8? Good. That means we have a critical number about here. So at the top, we have a critical number at 1 over the cube root of 2. I'm not going to write that number in. We have a critical number at 1. Is it correct that there were only two critical numbers for the derivative? The x-intercept is the origin. There we go. So is it the case that the only coordinates of the points, yeah, forget about that negative 0.577. I was thinking of a previous question. It is over here, this is approximately negative 0.79, the critical number. Is that better now, Haley? Okay, I was looking at something else I think I had in my head from a previous question. Now, when you look at your first derivative chart, you should notice that from negative infinity to the first critical number of negative 1 over cube root 2, which is approximately negative 0.79, the first derivative was positive. Correct? You should notice that in your second interval, from that negative 1 over cube root of 2 all the way to the only other critical number, the first derivative was negative, which means the function is decreasing. And then, I believe, and Dan, you're on top of this, so you can confirm, from 1 to infinity, the function was decreasing as well. Okay, so how do you draw this? I'm going to give you a minute to see if you can sketch a function that is asymptotic to those asymptotes, that goes through those 2 points, and that follows the behavior at the top of the screen. There's no way I can ask you to show me, well, I could ask you to show me your work, you'd have to send it, but if you figure it out, I want to know that you figured it out, though. I'm not going to put you on the spot and ask you to describe it. So I'm going to give you a minute or so to try that. Aiden's got it. Aaron thinks he has it. Dan thinks he probably has it. Allison thinks she has it. I think it's, well, I don't want to say obvious. When I say I think something is obvious, don't be offended if it wasn't obvious to you. But I think it's easier to figure out that this part must look like that. It has to look like that. That's the only way you can have a decreasing function couched in the corner of 2 asymptotes. The other part is trickier, but it's going to look something like this. So how many of you had that in your head? Okay, good. Now, we're pretty much done. We can take a look at this graph on the calculator in a second, but I want you just to think about for next week. There's something happening someplace here, isn't there? There's some twist. It's actually an inflection point that's happening there. It's where the function left to right stops having this kind of curve to it and all of a sudden has this kind of curve to it. And that's going to be related to the second derivative. And that's going to be something that we're going to have to worry about next week. And again, as I said, I think what I want to do is just do one lesson next week on Monday. We've got so much time in this course for me to do that. I think we need to slow down and just take our time with some of this stuff. Help me out here. Was it y equals x over x cubed minus 1? Good. Let me get rid of this stuff. Make it a little bit more visible. And we'll zoom in a bit. There's definitely some funny business going on in this region, but you can see that what we sketched is pretty darn close to what it should be. It looks like there's, as well as there being an inflection point right here, it looks like there's some kind of inflection happening here. Anyway, we're able to come up with a pretty decent picture of the graph. And by the way, this may not look the same because it's scaled differently. This lesson, everybody, was really about horizontal asymptotes. And that's what your assignment is concerning. We're not going to do example 3 today. We're going to finish it on Monday. So in terms of the assignment on page 222, I'm going to have to check. Give me a minute. You can get started on it. I'm going to check, and I'll get back to you on which of these you do not need to know how to do. It's probably going to be 5. Yeah, it's number 5. So we're talking here about just numbers 2, 3, and 4. And you know, the A, C, E, G, etc. thing. It's up to you. Do some from each question. If you need help, let me know. And there's only about 5 minutes left in class, so.